Okay. Hello everyone. This is Siddhartha Pramanik. I am a research scholar from the Department of Mathematics, IIT Kharagpur. So this is the live interaction season for week 5. So if you have any doubts, you can ask by unmuting yourself or by writing it in the chat box. So if you have no doubts, now I can start solving some sample problems regarding the contents of week 5. Meanwhile, if you have any doubts, you can ask. So let me just summarize the contents of week 5 first, then I will come to the problems. So in week 5, we have basically learned about the theorem, namely Cauchy's theorem. So in the lectures, you have saw the proof in case of abelian groups, but this is true in general. We will see later. Also, we have saw one more theorem, which has a name. Let's say G mod Z theorem. So in the problems, the professor has done this. And other thing is, we have saw lots of things about symmetric groups. So these are the main three topics of this week. So basically, I want to do this season only on symmetric groups so that you people can have a comfortable in doing calculations in the group symmetric group isn't. Okay. So in symmetric group, we already learned about how to write the elements of the symmetric group, right? By using the cycle notations. So let me also write down here. Okay. So the first problem, it is very basic. So let sigma be the cycle, let's say the n cycle belongs to the group S, let's say R. So it is an n cycle in the group SR. We okay VA n cycle. So this is a group element. So what is the inverse of this element? Then what is sigma inverse? So sigma also belongs to SR. That means sigma inverse also belongs to SR. So it can be written as uh, product of disjoint cycles, right? So what is that? So can you guess what is sigma inverse? So basically, sigma is a function from 1 to up to r to 1 to up to r, right? Not only a function, it is a bijection. So sigma inverse, it is the inverse function of this. So can you find sigma inverse from sigma? So you just need to find the inverse function of sigma. Okay, so let me write sigma as in the matrix notation. So under sigma, where uh, okay, not in this notation. So let's say a1, a2 up to an, because all other indexes are fixed by sigma. So under sigma, our a1 goes to a2, right? And a2 goes to a3. And an, this goes to just a1. So from this, we can just write sigma inverse. So it is also like an. So we need to find the images of a1, a2, an under sigma inverse. Okay. So what is the pre-image? So okay, we need to find sigma inverse a1, right? So that means this is the pre-image of a1 under sigma. And what is that? So pre-image of a1 under sigma is an. So it is an. Similarly, pre-image of a2 is a1. So continuing this, you can see the pre-image of an. What is pre-image of an? Can you see? Yes. So pre-image of an is an minus 1. Correct. So you have the function now. Now let's try to write it in the cycle notation. So first start with a1. So a1 goes to an. Okay, okay. Let's do it easily. Okay, let's write one more term so that people understood it better. And here we have an minus 1. So what is the pre-image of an minus 1 under sigma? Yes. So it is an minus 2. So let's start with an. So an goes to an minus 1 and an minus 1 goes to an minus 2. So continuing this, you can see here a2 goes to a1, and since a1 goes to an, so our cycle is closed here. Okay, so you can verify that inverse of sigma means inverse of this function is the same as this function. So it will be useful. That's why I am mentioning it clearly. So do you have any doubt in this? Okay, so let's move on. So just remember, if you have a n cycle like this, then uh, okay, let me prove it. And prove that sigma inverse is just an n minus 1 a2 a1. So the conclusion is, if you have an n cycle, then its inverse is also an n cycle, and you have just to write it in the reverse way. Okay, so we have written this in the reverse way or in the reverse order. Okay, let's move on to next problem. So let beta equals to the cycle 1, 2, 3 times the cycle 1, 4, 5. Okay, so this is some element of Sn. Let's uh, let's not worry about n, that is not important. Then write beta power 99 in the disjoint cycle form into the disjoint cycle form. Okay, so beta is an element of some Sn. So beta power 99 is also an element of the permutation group Sn. So it has some disjoint cycle form. So we have to find that disjoint cycle form. Okay, I hope you have understood the question. So we need to first find beta to the power 99, right? So we can't just multiply beta with itself 99 times. So there should be a more convenient way of doing this, right? So our group Sn is a finite group. So every element is of finite order. So let's uh, first find the order of beta. So can you say what is the order of beta? Anyone? So recall, if you have an element, yes, anyone have any answer? Okay. Recall, if sigma is an element of Sn, and if we write sigma as a disjoint cycle form, then order of sigma is just LCM of order of sigma 1 up to order of sigma r. So we need this disjoint cycle form to calculate the order, right? Because order of an n cycle is n. That was done in the lectures itself. So we need to find just the disjoint cycle decomposition. Then it will be easy to compute the order. So let's find what is the now see that it is not disjoint because the index 1 is common in both cycles. Okay, so let's multiply this both cycle, then let's see what we will get. So in the right hand side 1 goes to 4 and in left side 4 is not there, so 4 goes to 4 itself. So that means 1 goes to 4. Now in right hand side 4 goes to 5, but here 5 is not there, so 5 is fixed. So 4 goes to 5 under the multiplication. Now in the right 5 goes to 1 and left 1 goes to 2, so 5 must go to 2. Now 2 is not here, so 2 is fixed, means 2 goes to 2, and here 2 goes to 3, so in the product 2 goes to 3. Now in the right hand side again 3 is not here, so 3 is fixed, and in the left 3 goes to 1, so we can close this cycle. So beta is a 5 cycle, hence order of beta is 5. So now what is beta to the power 99? So it is beta to the power 95 plus 4, that means beta to the power 95 times beta to the power 4. But beta, okay, order of beta is 5, that means beta to the power 5 is equals to identity, right? So beta to the power 95, it is also identity. So we have beta to the power 4. So beta to the power 99 is equals to beta to the power 4. So we need to find beta to the power 4 first. But you can observe, since beta to the power 5 is equals to identity, let's multiply beta inverse both sides. So beta to the power 5 times beta inverse is equals to identity times beta inverse. So this implies beta to the power 4 is same as beta inverse. So ultimately, we need to calculate beta inverse. So you can see we have reduced the problem step by step. So we first have find order of beta. Then from that, we have simplified beta to the power 99 as beta to the power 4. And again, we have simplified it as beta to the power 4 is equals to beta inverse. So now beta is a 5 cycle. And in the first problem, we know how to compute inverse of an n cycle. So we just need to write it in the reverse order, right? So let's do that. So this is our beta. So let's try to write it in the reverse way. So 3 goes to 2, 2 goes to 5, 5 goes to 4, and 4 goes to 1. So that is the answer. And it is a cycle. So it is in the disjoint cycle form. So we don't have to do anything. Is it okay? Okay. Let's move on to another problem. So problem number 3. So let beta equals to the cycle 1, 3, 5, 7, 9, 8, 6 multiplied with the cycle 2, 4, 10. Okay. Then the question is, what is the smallest positive integer n such that beta to the power n is equals to beta to the power minus 5. So beta is some element in a permutation group. So we need to find a smallest positive integer n such that beta power n equals to beta power minus 5. So can you try it on your own by using the previous method in the previous problem? Okay, so let's find the order of beta first. So see that beta is product of two cycles, and both cycles are disjoint, right? So it is in disjoint cycle form. So we can easily calculate the order of beta. So what is order of beta? Anyone? Is it? So order is the product of order is the LCM of the order of other cycles. So this is your sigma, and this is your disjoint cycle form. Means this sigma is our disjoint cycles. So order of sigma is LCM of order of sigma 1, order of sigma 2, dot dot up to order of sigma r. So this is an 7 cycle and this is an 3 cycle. So this has order 7, this has order 3, and LCM of 7 and 3 is 21. So LCM of 7 and 3, it is 21. So this implies beta power 21 is equal to identity. So now we need beta power minus 5. So let's multiply this thing in the both sides. So this implies beta power 16 equals to beta power minus 5. And since 21 is the smallest positive integer such that beta power 21 is identity, so 16 is the smallest positive integer such that beta power 16 equals to beta power minus 5. So 16 is the smallest positive integer such that beta power 16 equals to beta power minus 5. Okay, I hope you have understood this. Okay, let's move on to another problem. So all these problems are I have collected in a sequence so that you feel comfortable in doing calculations in this group SN, because this group is very important. You will see later what is the reason behind that. Okay, so let beta uh, is a 10 cycle. Okay, so the question is, for which integers m, beta power m is a 10 cycle? Yeah, can you try it? So beta is a 10 cycle, right? Beta is a 10 cycle. So order of beta is 10. So we know if G belongs to some group and order of G is n, then we have saw how to find order of g power n. We have saw some formula, right? So if you have attended the live season 2 of mine, then I have done this. So this is basically n mod GCD of n comma m. So you should keep remember this formula. So basically, we need to find m such that beta power m is a 10 cycle. So basically, order of beta power m is also 10. So let me write. We need to find m such that beta power m is a 10 cycle. So that means order of beta power m is equals to 10. Okay. So let's write the formula. So order of beta power m is order of g is n here, and n is 10 in our case. So it is 10 comma GCD of 10 comma n. So this implies and this left hand side is also 10. So let's write it. So 10 equals to 10 by GCD of 10 comma n. So this means GCD of 10 comma m is equals to 1. So what can you say about m? So m is basically an integer which is co-prime to 10. Hence, m is, or let's say, relatively prime to m. Prime to 10. So, for example, it can be 3, 7, 9, 11, 13, all these things, which has GCD with 10 is 1. So all these elements has order 10, and that will be a 10 cycle. So I hope it is okay for you. Okay, let's look at a problem which is little bit difficult from this, but it can be done. It is not that much difficult. So let beta be an element in the group S7, means the permutation group on n letters 1, 2 up to 7, and given that beta power 4 is the cycle 2, 1, 4, 3, 5, 6, 7. Then we need to determine beta. So beta is an element of S7 in which beta power 4 is given, and it is a 7 cycle. So we need to determine what is beta. Okay, so I hope you have understood the question. So let's first try to determine what is order of beta. So given beta power 4 is a 7 cycle. So that means order of beta power 4 is 7. So beta power 4 whole power 7 is the identity element, and this implies beta power 28 is the identity element. So from this we can say order of beta must divide 28. So what are the possibilities? So order of beta equals to 1, equals to 2, it can be 4. So basically it are the all positive divisors of 28. So it can be 7, it can be 14, or it can be 28. Okay, now let's try to discard one by one. Now this cannot be 1 because beta is non-identity element, because beta power 4 is non-identity element. Similarly, it cannot be 2. Okay, so let me write. Now order of beta, it cannot be 1, 2 or 4. The reason is beta power 4 is not equals to identity. But if it is 1, 2 or 4, then beta power 4 will be identity element. But that is not possible. So we have discarded this first 3. Now we have 3 more choices. Let's see what are the cases. Now, okay. Now if order of beta equals to 14, then what can you say? So which elements in S7 has order 14? So if alpha belongs to S7 has order 14, then what is the disjoint cycle decomposition of alpha? First of all, it cannot be a 14 cycle because we are in S7, right? So alpha cannot be a 14 cycle. So alpha cannot be a 14 cycle. So what are the other possibilities? So if alpha is written in the disjoint cycle form, then 14 equals to, okay, then 14 which is equals to our order of alpha, it must be LCM of order of alpha 1 up to this. So what are the possibilities of order of alpha i's? So it must divide 14, right? So order of alpha I must divide 14. So order of alpha I is 1, 2 or 7, because it cannot be 14, because it cannot have a 14 cycle. But if some alpha I has order 7 and some alpha j has order 2, this is also not possible because alpha I and alpha j are disjoint cycles. So you have total 7 plus 2 means 9 indices, but we are in S7. So we have only 7 indices. So this is also not possible. So then beta is either a 14 cycle or beta is, okay, let me write disjoint, okay, let me write clearly, uh, or in the disjoint cycle form of beta, there are 2 cycles and 7 cycles. So this is also not possible. So none of these two cases, either a 14 cycle or product of 2 cycles and 7 cycles, none these cases are possible. So none of these cases are possible. So order of beta is not equals to 14. Okay, did you understood this? If you have any doubt, you can ask me. So order of beta cannot be 14. Now, in this similar argument, we can say order of beta cannot be 28. In a similar logic, you can try to argue by on your own and write out the details. So what are the possibilities? 1 2 4 are already discarded, 14 and 28 are also discarded, 7 is left. Hence order of beta is 7, right? So this implies beta power 7 is equal to identity. But our goal is to determine beta, and we have given beta power 4. So here what we will do, we will multiply beta in both sides. So beta power 8 is equals to beta, but in the left hand side it is equals to beta power 4 square. So beta is same as beta power 4 square, and beta power 4 is given. So this implies beta is equals to, okay, let me write what is beta power 4, 2 1 4 3 5 6 7. So 2 1 4 3 5 6 7. So we need to multiply it itself. So again 2 1 4 3 5 6 7. So let's multiply it. So remember that we multiply cycles from right to left. Means we first look at in the right, then we look at it in the left. So let's start with 2. So 2 goes to 1, and here 1 goes to 4. So 2 goes to 4. Now let's see 4. 4 goes to 3. 3 goes to 5. So 4 goes to 5. Now let's see 5. 5 goes to 6. 6 goes to 7. So 5 goes to 7. Now let's see 7. So 7 goes to 2 and 2 goes to 1. So 7 goes to 1. So let's see 1. 1 goes to 4. 4 goes to 3. So 1 goes to 3. So let's see 3. 3 goes to 5. 5 goes to 6. So 3 goes to 6. So let's see 6. 6 goes to 7 here. 7 goes to 2. So 6 goes to 2. So we can close our bracket. So this is our beta. So is it clear? Just think for a moment if you have any doubts. Okay, I hope others has also understood this. So let's see problem number 6. Okay, now let's try to find uh, how many elements of a fixed order are there in the group of permutations. So let me start with a simple problem. So how many elements of order 4 are there in S6? So you need to determine the total number of elements in S6 which has order 4. Okay, let's do a little bit simpler problem first. Let's try to find elements of order 5 in S7. So we need to determine how many elements in S7 are there which has order 5. Okay, so for this, let me write. First, we need to know how the elements of S7 of order 5 looks like. So I mean, what is the structure of elements of order 5 in S7? So we need to first look at that. So we need to determine their cycle structure. So that means what is their cycle structure? So if we write that element in disjoint cycle form, how it can be look like? So if alpha belongs to A7 such that okay, order of alpha is 5, then the disjoint cycle form of alpha is the means the cycle structure disjoint cycle form of alpha equals to, so if we write it in the disjoint cycle form, let's see alpha 1 up to alpha r, so how it can be looked like. Since order is 5 and we are in S7, so it must be a 5 cycle. So alpha, disjoint cycle form of alpha is just a 5 cycle, right? So it cannot be product of any other cycles. It is just a 5 cycle. So only 5 cycles has order 5 in S7. So we need to determine how many 5 cycles are there in S7. So hence alpha has the form, it is a 5 cycle means A1, A2, A3, A4, A5. So it is a 5 cycle. So we need to determine how many 5 cycles are there. So basically alpha is a bijection. Bijection of one, okay, let me write it in a bigger way. So you have 1, 2, 3 and so on up to 6, 7. Here also you have 1, 2, 3 up to 6, 7. So okay, basically it's a 5 cycle and this AIs belongs to 1, 2 up to 7. So okay, we don't need this thing here, my bad. So for A1 we have 7 choices, right? Now A2 cannot be same, so we have 6 choices. Yes. So and for A3 we have similarly 5 choices. So this has 4 choices and this has 3 choices. But you can see 5 cycle, we can write this as, so it is a cycle, right? So instead of starting with A1, we can also start with A2 or also from A3 or from all the other things. So it is same as, so A1, A2, A5. So this cycle is same as A2, A3, A5, A1. So we can start with A2 also. Similarly, we can start with A3. We can also start with A4. So there are 5 things. So we can start with A3. We can start with A4. We can start with A5 also. All these 5 cycles are same. So what is the total possibilities? So the total number of 5 cycles is equals to, so we have 7 choices. These choices are independent, so we need to multiply them. So 7 times 6 times 5 times 4 times 3. But we have these repetitions also, right? So we need to uh, so we need to divide it by 5 because we have 5 repetitions for each case. So this is the number of your 5 cycles in S7. So this is equal to 7 times 6 times 4 times 3. Okay, so this is the final number. So I hope you have understood this. So you just need to understood exactly one example of this type. So then you can do the other problems of this type. So this is important. So if you have any doubt, you just ask now. So we have first look how the elements of order 5 in S7 looks like. So it is just a 5 cycle. So we need to determine the total number of 5 cycles. So how many elements of this type are there in S7? So it has 7 choice, it has 6 choice, up to so on, it has 3 choice. But each 5 cycle can be written in this 5 ways. So these are all same cycle. So we need to count distinct 5 cycles, right? So we have divided this one by 5. Okay, I hope this is okay. So let's see a similar problem of this type. So how many elements of order 4 are there in S6? So can you quickly try it and give me an answer? Let's try for a few minutes. 6 into 5 into 3. Uh, no, you have missed something. Okay, let me do it. So first of all, we need to find how the elements of order 4 in S6 looks like. So let alpha belongs to S6 such that order of alpha is 4. So what is the disjoint cycle form? Then what is the disjoint cycle form of alpha? First of all, it can be a 4 cycle. That is okay. So alpha can be a 4 cycle. A1, A2, A3, A4. But here we are in S6. So alpha can be a product of a 4 cycle and it is product of 4 cycle with a 2 cycle. Okay, it should be disjoint. So A5, A6. So this 4 cycle has order 4 and this permutation this is product of two disjoint cycles. One is a cycle of length 4 and one is cycle of length 2. This has order LCM of 4 comma 2. This is 4. So alpha can be this thing also. So probably you have missed this part. So you need to be careful. So you need to find all possible cycle structure. So in this case, how many elements of this type are there? So this has 6 choice, this has 5 choice, this has 4 choice, this has 3 choice. And this fourth cycle can be written in 4 ways, because you can start it with A2 or A3 or A4 also. So this is 6 times 5 times 4, 3 by 4. But in this case, you have 6 choice, here you have 5 choice, here you have 4 choice, here you have 3 choice. So here you have 2 choice and here you have 1. Since it is a 4 cycle, so you need to divide by 4, and it is a 2 cycle, so you need to divide by 2. So let's write it. So this is 6, 5, 4, 3 by 4, 2, 1 by 2. So total number is this plus this. So the number of elements of order 4 in S6 equals to, so this we can cancel out. So this and these are same. So 2 times 6, 5, 4, 3 by 4. So this is 2 times 6 times 5 times 3. So is it okay? Yeah, okay. So I hope it is fine for others also. So let's do one more problem in of this type. So that it is clear for you, and so that you can do it by on your own. So how many elements of order 2 are there in S6? So first try on your own and give me an answer, then I will give you the correct solution. Just try for a few minutes. Yeah, anyone? Any answer? Okay, let me do this. So as usual, we need to see what are the possible cycle structures of elements of order 2 in S6. So the possible cycle structures of elements of order 2 in S6 are, so it can be a 2 cycle, it can be a product of two cycles, and it has to be disjoint, and it can be product of two cycles, three disjoint 2 cycles. A5, 6. So it is a 2 cycle, it is product of two disjoint 2 cycles, it is product of three disjoint 2 cycles. Are there any other possibilities? No, right? So we need to find how many elements of this type are there, also how many elements of this type are there, and also for this type. So for this, A1 has 6 choice, A2 has 5 choice, and it's a 2 cycle. So it can be written as A2, A1. So both are same. So we need to divide by 2. So what about this one? So for A1 we have 6 choice, for A2 we have 5 choice, and A1 A2 is same as A2 A1. So as usual we will divide by 2. Now A3 has 4 choice, A4 has 3 choice, and it is a 2 cycle, so we will divide by 2. But we can, this is same as A3 A4 times A2 A1, because these are disjoint cycles, so they commute. So these two things are same, means these two permutation. So again we need to divide it by 2. So we need to exclude the similar elements because we are counting distinct elements. So the last case, let's do it similarly. So A1 has 6 choice, A2 has 5 choice, this has 4 choice, this has 3, this has 2, this has 1, all are 2 cycles, so we'll divide it by 2. But these 3 cycles are disjoint, so we can write it as A3 A4 first, and A1 A2 A5 A6. So we can permute these two cycles in 3 factorial ways, and all our 3 cycles are product of 2 cycles are same. So we need to divide that one. So it should be 6 times 5 by 2, 4 times 3 by 2, 2 times 1 by 2, whole divide by 3 factorials. Is it okay? So the total number of elements of order 2 in a 6 equals to sum of this and this, the last one. So 6 by 5 by 2 plus, okay, let me, so 4 times 3 by 2 times 1 by 2 times 1 by 2 by 1 by 3 factorial. So the first one is 15. So we can cancel this with 4 and this with this. 3 times 5 times 3, it is 45. So 3 factorial and 6 cancelled out. 4. So it is just 5. Sorry, it is just 15. So this is 75. So is it okay? Do you have any doubt in this? Okay. So let's do one more problem related to this so that it becomes clear to you more. So how many elements of order 10 are there in S? So you just try it on your own. Spend a few minutes. So what are the possible cycle structures are here? So the possible cycle structures of element of order 10 in S10 are, so look, how can you write 10 as LCM of elements? So it is just LCM of 10 comma 1 or LCM of 10 comma 2 kind things, or LCM of 10 comma 5, or LCM of 2 comma 5. but we are in S10, so we have only 10 indexes. So we can have a 10 cycle. We cannot have 10 cycle product with a 2 cycle. We cannot have. Similarly, we cannot have product of 10 cycle and product of 5 cycle. It has to be disjoint, right? You cannot have this type of things. We can have a product of 2 cycle and a product of 5 cycle. So the possibilities are a 10 cycle, A1, A2 up to A10, and it is a product of a 2 cycle and a product of 5 cycle. So these are the only possibilities in S10. So we need to determine how many 10 cycles are there and how many elements of this type are there. So number of 10 cycles is very easy. This has 10 choice, this has 9 choice, this has 1 choice. And we can write this 10 cycle in 10 ways. So 10 factorial by 10, which is 9 factorial. And what about this? So this one has 10 choice, this one has 9 choice. It is a 2 cycle, so we have to divide by 2. This is 8 choice, 7 choice, 6 choice, 5 choice, and A8 has 4 choice. But it is a 5 cycle, so we need to divide it by 5. So the answer is 9 factorial plus 5 into 9 times 8, 7, 6, 4. So this is actually 9 factorial plus 9 factorial by 3 factorial. This is the final answer. Okay, did you understood this? Or if you have any doubt, you just ask me now. It will be better for you. Okay. So did you understood this cycle structure? Okay, so we have only a this one A8 goes to okay. Okay, let me write it clearly. So it is a 5 cycle. So A3, A4, A5. Oh, sorry, it should be A7. Okay, so it's my bad. So it should be A7 because it's a 5 cycle. So okay. So this is a choice. This is 4 choice. Okay, anyone? Anyone else? Okay, so then let's move on to another problem. So this is question number 10. So this is a different problem, but it's interesting. So suppose beta and gamma are elements of S4 such that beta times gamma, this is given as 1, 4, 3, 2. So it's a 4 cycle. And gamma times beta, it is given as 1, 2, 4, 3. So it is also a 4 cycle. Now assume, so beta gamma are elements of S4 and they are bijections, right? Means they are functions. So under beta, 1 goes to 4. So the problem is determine beta and gamma. Okay, I hope you have understood this. So beta and gamma are two elements of S4. So that means they are functions from 1 to 4, bijective functions from the set 1, 2, 3, 4 to 1, 2, 3, 4. Also we have given beta times gamma means beta compose gamma and gamma compose beta. Also they have given under beta 1 goes to 4. So we need to determine the functions beta and gamma. So first observe that beta gamma and gamma beta, they are not equal because here 1 goes to 4 and here 1 goes to 2. So these two functions are not same. So that means b, okay, let me write, observe beta gamma not equals to gamma beta. So beta and gamma cannot be disjoint, because if they are disjoint, then they must commute, right? So this is one property we have learned in the lectures. So let's write beta gamma in the matrix form. So here 1, 2, 3, 4. So under beta gamma, 1 goes to 4, 2 goes to 1, 3 goes to 2, so 4 goes to 3. And also let's write gamma beta in the matrix form. So under gamma beta, 1 goes to 2, 2 goes to 4, here 3 goes to 1, so 4 goes to 3. So we need to determine beta. So let's write the matrix first, and also we need to determine gamma. So given that beta of 1 is 4, so let's just write that. Okay, now using this information we need to find these other entries. So how can we do that? So observe that beta of 1 equals to 4, this is given. So let's apply gamma. So what is gamma beta of 1 is equals to gamma of 4, right? So gamma beta of 1, so under gamma beta 1 goes to 2. So gamma of 4 equals to 2. So let's write this. So gamma, under gamma 4 goes to 2. So again let's play the same game. Gamma of 4 equals to 2. So let's apply beta. So beta gamma of 4 equals to beta of 2. So what is beta gamma of 4? Under beta gamma 4 goes to 3. So beta of 2 is equals to 3. So let's put it here. Under beta 2 goes to 3. So let's do the same thing again. Beta of 2 equals to 3. This implies we will apply gamma. So gamma beta of 2 equals to gamma of 3. So what is gamma of 3? It is gamma beta of 2. So under gamma beta 2 goes to 4. So it is equals to 4. So under gamma 3 goes to 4. So gamma of 3 equals to 4. This implies, let's apply beta. Beta of 4 is equals to beta gamma of 3. So what is beta gamma of 3? Beta gamma of 3 is 2. So it is, so beta of 4 is 2. So let's write it. So beta of 4 is 2. But beta is a bijection. So 3 has only one option, and that is 1. Right? So we have completely found beta. Now let's see gamma. So beta of 4 equals to 2. Let's apply gamma. So gamma beta of 4 equals to gamma of 2. So what is gamma of 2? It is gamma beta of 4. So gamma beta of 4 is 3. So it is 3. Under gamma 2 goes to 3. So let's write it. So again gamma is a bijection. So we have only one choice. So 1 goes to 1. So let's write it in the cycle forms. So let's start with 1. Here 1 goes to 4. Again 4 goes to 2. 2 goes to 3. Finally 3 goes to 1. So we can close it. And what is gamma? It is just 1 is fixed here. So we don't need to write 1. So let's start with 2. So 2 goes to 3. 3 goes to 4. Yes. So 4 goes to 2. So we can close the bracket. So this is the final answer. So is it okay? Yeah, okay. So okay. Let's move on to another one. It is 11. So this is a different type of problem. Let's see it. So for n greater equals to 3, define h equals to this set of all those elements of the group Sn such that alpha of 1 equals to 1 or 2 and alpha of 2 equals to 1 or 2. So this is a subset of Sn. So prove that H is a subgroup of Sn, and also determine what is the order of H, means the cardinality of the set H. Okay, so we have assumed n is greater or equals to 3 and we have defined a set H which is a subset of Sn. So what is this set? This is set of all permutations of Sn under which 1 goes to 1 or 2 and also 2 goes to 1 or 2. But observe that if 1 goes to 1, then 2 has to go to 2 because these are bijections, right? So that is one important observation here. So let's see a solution of this. So first we need to prove H is a subgroup. So H is a subgroup of Sn. So let's prove this. So to prove a subgroup, we need to prove three properties. First one is the closure. Second one is the existence of identity. And third one is the existence of inverse element. Okay, so let's check one by one. So let alpha and beta are two elements of H, right? So then under alpha, the set, what is the image of this set 1, 2? Under alpha. This has to be one same set, right? This set maps to 1, 2 itself. Because under alpha, uh, alpha of 1 is equals to 1 or 2, alpha of 2 is equals to also 1 or 2. So alpha of 1 comma 2 has to be 1 comma 2 because alpha is a bijection. So this is same for beta also, right? Hence under alpha beta means the composition of alpha and beta. So this is also a bijection. So for this case also it is same. So alpha beta of 1 equals to 1 or 2 and alpha beta of 2 is also 1 or 2. So we have used that composition of two bijection is again a bijection. So this implies alpha beta must be an element of H. So this proves the closure property. Okay. So second is the identity element. So identity element of Sn is the identity function on of the set 1 to up to n. Now the identity E of Sn clearly is in H. Why? Because under identity 1 goes to 1 and 2 goes to 2. Right? So E has to be in H. So identity is very clear. Now the inverse. Now if alpha belongs to H, then so here you have the set, let's say 1, 2 up to n. Here you have the same set 1, 2 up to n. This is your function alpha. So this is your reverse function alpha inverse. So under alpha 1 comma 2 maps to 1 comma 2. So alpha inverse does the same thing, right? So alpha of 1 2 is the same set 1 2. So this implies alpha inverse of 1 comma 2 this means the inverse image of this set under alpha. Inverse image of this set 1 comma 2 under alpha. Okay, so I hope this is clear. So this means alpha inverse is also in H. So hence H is a sub. So we have proved the first part of this problem. The second part is the order of H. What is the order of H? So can you do it? Can you determine what is the order of H? Just try for a few moments. It is just a basic counting problem. Just try it for a few minutes. Yeah, anybody has any answer or any idea how to find order of H? You can unmute yourself and speak. Or if you have any doubts so far, then you can ask. Okay, so let me do the second part, which is the order of H. So determine order of H. So let's say this is your set 1, 2, 3, 4 up to n. This and let's take the same set 1, 2, 3, 4 up to n. So let alpha belongs to H. Then what alpha does? So under alpha, okay, let me take another color. So this is your alpha. So under alpha, one has two choices, right? Which is either 1 or 2. So if you send 1 in any one of the choice, then 2 has only one choice, right? Because 2 also maps to 1 or 2. But in case of 3, you can map it to any n minus 2 elements, correct? So for 4, you can map it to n minus 3 possibilities. So similarly, for n minus 1, you have two choice, and for n, you will left with only one choice. So what are the total number of possibilities? So we need to take the product of all these choices, right? So order of H is 2 times 1 times n minus 2 times n minus 3 up to 2, 1. So what is this? This is just 2 times n minus 2 factorial. Yes, 2 times n minus 2 factorial. So this is the order of H. So one question for you, that we have already proved that this set is a subgroup of Sn. So I want you to check that is it a normal subgroup of Sn? Just try. Is H a normal subgroup of Sn? Just quickly try. Just take some sample elements from Sn and sample elements from H and try to see sigma, gamma, sigma inverse belongs to H or not. Yeah, do you have any answer? Yeah, anyone? So is H a normal subgroup of Sn, or do you have any guesses? So observe that. So if n equals to 3, then what is H? We know S3, right? So S3 is just identity 1 2 1 3 1 4 1 2 3 1 3 2. And what is H in this case? 1 4 2 3. Is it correct? So first observe this set. So under H, an element of H should map 1, either 1 or 2. Same for 2. So this element does not sense 1 to either 1 or 2. It is 4, right? So it cannot be in the set. So this element 1 2, it must be in H. In fact, this is the only element is in H, non-identity element. You can check it, because under this cycle 1 3, 1 goes to 3, so it cannot be. So 1 4 similarly cannot be. This cycle 1 2 3, 2 goes to 3, so this is also not possible. Similarly, this is also not possible. And if you have seen in the lectures, oh okay, okay, yeah, you are correct, yeah, okay. So in that case also 2 3 does not belong to the set H. So H is the set identity and the 2 cycle 1 2. And from the lectures you can see that H is not normal in S3. So in general, okay, let me write down it. Let me put it as a remark. You will see this in the upcoming lectures. So for n greater equals to 5, there are only no, that is already done. So I'm saying for n greater equals to 5, there are only 3 normal subgroups of Sn, and they are obviously the singleton set identity, the trivial group. Second one is Sn itself, and the third one is An. So this is known as alternative group on n symbols. So in the next week, you will be introduced with this subgroup. So let's wait for this, and this is a big result. I hope in the upcoming lectures you will see this. Even if you will not see this, I will do in the tutorials in that case. So the point is that H does not fall in any of these 3 categories. So you will realize it when you will be introduced with the subgroup A. So we have done 11 problems. Let's do number 12. So this is a problem based on what we have done till now. So this is to just check. You can do these calculations on your own or not. So let alpha equals to this permutation 1, 3, 5, 7, 9 times 2, 4, 6 times 8, 10. So if alpha to the power m is a 5 cycle, what can you say about m? So just try it. So given alpha is a permutation and it is given that alpha power m is a 5 cycle. So what can you say about m? Yeah, do you have any idea how to approach? Yeah, anyone? So how to approach this? What should be your first step? So observe that alpha power m is a 5 cycle. Okay, let me write it. Observe alpha power m is a 5 cycle. So order of alpha power m should be 5. And we know how to compute order of alpha power m from order of alpha, right? So we need to compute order of alpha first. So let's compute it. Or can you say what is order of alpha? So this is our alpha, and this is product of 3 cycles. So first one is a 5 cycle, second one is a 3 cycle, third one is a 2 cycle. You can see that this yes, you're correct. These 3 cycles all are disjoint. So it is in disjoint cycle form. And in disjoint cycle form, we know how to compute the order. It is the LCM of orders of this one, order of this one, and order of this one. So it is LCM of this is 5 cycle, so it is 5. Second one is a 3 cycle, so it is 3. And third one is a 2 cycle. So order of alpha is 30. So using this, what is order of alpha power m? This is just 30 divided by GCD of 30 comma m, which is our formula. You can go back to live season 2 of mine, and I have done a proof for this. You can check. So all the lectures are given in the Excel sheet. I hope you have watched. So this implies this is 5, right? So let's write it. So GCD of 30 comma m should be 30 by 5. So it is 6. So from this, what can you say about m? So 6, 6 is the GCD, right? So 6 should divide both 30 and m. So that means m should be multiple of 6. It is clear. So that is the only thing. So m is multiple of 6. But you have to observe that 30 is also multiple of 6. It is 6 times 5. But can m equals to 30? Alpha power m, it is a 5 cycle. So m cannot be 30, right? Because alpha power m means alpha power 30 is identity. So we should have put much restriction. M is multiple of 6 and yes, it can be 6, 12, 18, 24, but not 30. So it cannot be a multiple of 30. So let me write this. And m is not a multiple of 30. Yeah. So did you understood this? Okay. Let's do one more problem. So basically in this season we have done all problems related to the symmetric group, right? And cycle rotations. So we have not done anything related to Cauchy's theorem or G by Z theorem. So let's see one problem related to G by Z theorem. So first I should recall what is G by Z theorem. So recall the G by Z theorem. So it was done in the lectures, in the problem in which the professor done problems. So it says let G be a group. Now if the quotient group G mod ZG is cyclic, then the group G has to be an abelian. Remember, ZG is the center of the group. So it says if G mod ZG is a cyclic group, then the group G has to be abelian. Right? So in the lectures, I hope you have saw a proof for this. Now let's see problem related to this. So it is problem number 13. So let G be a group of order, let's say 15. Okay, then what is the order of the center of the group? Can you do it? So order of G is 15. You need to find order of ZG. So order of G is 15. So what is order of ZG? So hint is you have to use this theorem, G mod Z theorem. Uh, is it so? So you are wrong. Okay, so let's see why. So now ZG is a subgroup, first of all, right? Center is a subgroup of G. So by Lagrange's theorem, order of ZG must divide order of G. This is by Lagrange's theorem. And order of G is 15. So this implies order of G is a divisor, positive divisor of 15. So it can be 1, it can be 3, it can be 5, or it can be 15. So let's see which are the possibilities. So so uh, so my claim is order of ZG is either 1 or it is either 15. Okay, so okay, let me write order of ZG is 1 or 15. So that means it cannot be 3 or it cannot be 5. So if order of ZG equals to 3, then what is the order of this quotient? This is just order of G by order of ZG, right? So it is 5. Now you have saw that 5 is a prime number. So a group of prime order, yeah, any question? If you have any question, you can unmute yourself. Okay, so G mod ZG is a group of order 5, which is a prime number. So G mod ZG is a group of order 5, a prime number. But a group of prime number must be cyclic. So we have saw this in the previous week's lecture. Hence, G mod ZG is cyclic. So you apply the previous theorem. So G mod ZG is cyclic implies G is abelian. So by G mod Z theorem, G is abelian. But that implies G equals to ZG, right? So that will imply order of ZG is 15, but we have started order of ZG is 3. So this is not possible. So this is a contradiction. So order of ZG cannot be 3. So I hope this is clear for you. So in a similar way, you can prove that order of ZG cannot be 5, because in that case, this order of the quotient will be 3. That is also a prime number. So we can argue in the same way. So we have only two possibilities. Yes. So order of ZG is either 1 or it is either 50. So let me write it. Similarly, order of ZG cannot be equals to 5. So order of ZG equals to 1 or it is 50. So we are done. Okay. So in fact, we have started with a group of order 15. We can generalize this. So let me write down the general version. So I will put it as a remark. So if G is a group of order, let's say P times Q, where P comma Q are distinct prime numbers, then order of ZG is either 1 or it is either PQ. So the proof is exactly the same. So instead of 3 and 5, you have P and Q. So you can write down the details. Yes, so you can write down the details. So one warning is this above remark may not be true if P equals to Q. Here we have taken distinct primes, so that is important. So this may not be true for group of order P square. Okay, so that is also an interesting case. So you can look for it. Yes, yes. So that's why I put it. Yeah, I'm saying if it is equal, then this result may not be true. Okay. Yeah. So I hope you have understood what I have done so far. Do you have any doubt in this live season? Anyone? So I will upload this video in the YouTube. You will have the link and also these notes. And here is my website. If you have any doubt, you will found email ID of me in this website. You can mail me. So I am already over time. So thank you everyone for joining. We can end this season now. So you can leave.